Thank you very much, Danielle, Claudio as well. Thank you for the invitation for this time and the previous time. And actually, I have to say, I have enjoyed my participation here at RIBES over the last number of years. And this is a very good set of candidates for PhD. Hopefully very soon, the next few months, you'll get your degrees. And a lot of good work has happened. And for me, who started quite a number of years ago with very few people in this field, to see so many people, not only from this group, which is great, but many other groups around the globe working in this area is terrific. It's what I would like to see, because there's, as you presented yesterday, and some of the things today, there's a lot of work to be done. A lot of things we don't understand. It's a complex issues, and we need to decipher a lot of those things. So, great to see you all again. Okay, so we talked about limitations on fish passage devices, especially in structures. Is there any hope for the future for some of these things, or have we reached a dead end for efficiency and effectiveness for some of these structures? So is there some avenues that we can proceed with? And that's sort of going to be my emphasis on this. One more. Okay. So I think some of the points have been raised, but a lot of times it's good to re-emphasize them. So dam removal and river restoration is one of the hot topics, and it's a high priority, and I was happy to hear that EU is putting some priority on that, because there are a lot of structures there in Europe as well as other places, but especially in Europe with such high density, to remove items that are not used anymore, and not only remove them, but also help the river get restored. Maybe renaturalized to some extent, rewild, some other words that people are using. And there's a lot of opportunity there. And a lot of the work that needs to be done can go to that. And that has to be done very carefully and very well as well. It's not just blow up the dam and we're done, right? It has to be done very carefully. But some of these concepts of nature-like or nature-based solutions, that's what we call it today. Well, back in 1979, when you see the culvert slide, this one, it was my initial career move in this area, and we were up in the Northwest Territories in Canada, up in the Arctic, building a new highway. And that's what we came up with in terms of how do you put a culvert in the stream that you don't know much about its hydrology or much else, or its fish species or so on. So the idea was to take the culvert and wrap it around the stream up to at least some sort of a mean annual bankful kind of discharge, and put substrate in it to simulate the stream, although we were a little conservative, so the rocks that you see, they're actually larger than what the stream did, just to make sure that they stay in place. Well, not only it worked, because evaluated for Arctic grayling and other species, but it had a long lifespan. It's still there, even though the picture was taken in 2008, it's still working. While we had big floods on the same highway that washed out older culverts that were built not so much for fish or other things, just to get the water from A to B, and they were washed out and replaced by bridges, for example, in some cases, because of that. So other structures that apply this idea of nature-based, there's another one, the Churchill River in northern Manitoba, a very long structure. This river was diverted to another one, the Nelson River, for hydro purposes, and many decades later they put this weir to try and restore some of the river, but it has a ramp essentially for fish to go up. In Finland, they got a little pretty there with flowers and everything else all around them. And their latest project, which is under construction now, is in the Netherlands, this fish migration river. We were involved, Paul was there, and Claudio is actually partly there too. So the idea has taken off, maybe changed the name, but the idea goes back quite a few decades. And those are good things to replace if dam removal is not feasible or not possible, right? Now, when it comes to fish passage structure, since we're concentrating on that topic, I would divide them in sort of two major categories. These volitional ones that, fish go up on their own, they have to find their own way, or those that are handling fish in some way. So, and we have facilities for upstream and for downstream, and there's quite a variety of things that have been developed over several decades, or the last 100 years or so. And some of them are specific to eels, some are specific to other species. There's one here, for example, in Quebec, which was designed for sturgeon, this one. I think somebody else had a slide up there of this one. And you can combine them and so on. So people have done it around the world with these kinds of designs. But as I said earlier, a lot of times, without a lot of testing, without a lot of information, a lot of structures have been placed in there, and sometimes they work, sometimes they don't. We have a better chance with salmon than many other species. So that's one aspect. Now there's volitional structures for downstream passage, and Ole, for example, showed a good example from the Trans River, and for smaller structures, I think that those are very good solutions. But sometimes we have to deal with very large dams, and somebody else made the point, Bill Sarah, I think, made the point that, okay, these structures, these screens become very expensive to maintain, very expensive to build, and so on. So does it always work in some of these big dams? There's irrigation canals. It's not only dams that, you have a dam, but the main purpose of it is to divert water for irrigation purposes. How do you screen fish from the water that goes into the irrigation canal? All those things, as well as bypasses that help fish. So there's quite a variety of structures, and this is not all of them, right? The point I'm trying to make is there's quite a variety of things have been developed over the years for upstream and downstream, and some of them may not be structures per se, it may be flow, or managing flow to help fish go down, or sometimes up too. But this one is from the Columbia River, for example, and they can help salmon, in this case, again, smolts to go down in a safe way. But you still have to spill some water, right, to make that work. Another non-volitional in this case, we call it trap and haul, or trap and truck, or trap and transport, depending which term you like, is to find the fish somewhere close to the dam, lift them up, and transport them upstream, or the downstream too. You can actually barge them down or find other ways to transport them down. So that's another system. And this system usually is maybe more economical, better for very tall dams. When a fishway becomes so long, even for salmon, that maybe are they going to go all the way up, spend so much time to go from one end to the other, especially non-salmon species. So, but the challenges are there. How do you collect these fish? How do you guide them? And so on. So, and you can see facilities like that around the world too. So, just some overall comments on volitional and then non-volitional fish. I was going to look at both of them together because they have some commonality. First, you have to, if we're expecting to design any effective system, we need some good information on the biology, of course, the life history, and different species have different life histories, needs. What's their migratory behavior? When do they move? What flows? What temperatures? All those things are very useful, right? As well as something about their physiology and their abilities, swimming, jumping, crawling, whatever it may be. We need to understand all those abilities, otherwise we can't design for them, right? Of course, the hydrology and hydraulics and geomorphology actually very important as well to provide a basis for us to have a chance, a good chance to have a suitable design. We emphasized it again yesterday too. Maintenance and adaptive approach is very important. Maintenance is one thing, but you also have to, we don't know enough about many of these structures, so you always have to think, can I adapt this structure once it's built? Can I adapt it in a way of modifying the structure, or can I adapt it in a way of how it operates? Maybe play with the flow and so on, for example. And a lot of times, of course, nature-like fishways are based on a great principle, trying to mimic nature. But they also we have to be careful because there's been evidence in some cases that we didn't build them. They don't attract enough fish because of the way they were placed, for example. Or a lot of times, maybe it's easier for fish to go through, but they have a tough time finding and entering as well as exiting. So those are the kinds of things that apply to all systems. We have to be very, very principled about how to do this properly with enough data. And a lot of times we don't have enough data, so we're guessing many times, which doesn't help us when it comes to effectiveness and efficiency, I suppose. But of course, fishway effectiveness is a complex issue. It's not a simple, here the fish go from one to the other. It's complex interactions, complex parameters, several parameters. And we need a lot of rigorous studies. I call them ecohydraulic studies because they're trying to combine biology and hydraulics. Of course, good engineering, and again, economics play a role too. So a lot of times, at least way in the past, economics dictated what you're going to put there, and a lot of times you compromise the design because of the economics. So we can't afford to do that, otherwise we're going to have ineffective structures, essentially. So essentially what I'm suggesting is we can start with a reasonably good design and have this adaptive management in mind all along, and maintain the structure. Critical to evaluate it, and again, maybe we won't be able to evaluate everything, but if we have at least selected a few that we're going to evaluate comprehensively, then we can learn a lot about it. Operate it properly. A lot of times people don't build it and abandon it. Well, what do we expect in that case, right? What can we expect? And modify it as the information that comes in indicates. And the last point is important too. It takes years to understand what's going on. It takes years to find out what the fish need, how to find the structure or not, how to help them, guide them, whether it's upstream or downstream. So we cannot expect after either not monitor at all or monitor for a year or two and then we're done, kind of thing. It's not that easy. So, because we have a lot of experience with salmon, I think we have our best chance with salmon, Atlantic and Pacific salmon for that matter, to do a good design, whether it's evolutional fishway or trap and haul. And our nodes may be more or less adequate for that, but you still need the site specifics, which of course will differ from place to place. You can apply the basic principles, but you still need to study your site very well before you can actually have a good hope of succeeding. So, despite though a lot of these evaluations and there's still a lot of challenges and complexities. So, to understand it, long-term evaluations is very important, and we have very few of those, very few cases of those. But if we do it properly, there are examples, good examples, with very high rates of passage. And I'm giving you one of the best examples in the world, the Columbia River. It has been developed maybe in the last 100 years or so. People have had an adaptive management philosophy. They count in every salmon. They know every salmon where, not only the species, but stocks, because some subpopulations of the Pacific salmon, of the same species, go to different places. So they know who goes where, and more or less how many. They tag a lot of fish. It's very solid information, not only for 1 year, for decades. And then, of course, they adjust and so on. Now, you can't afford to do that in every river, I understand that, but at least in a few rivers, we should be able to do it for different species, because then we can actually learn a lot. So, very high percentages, 95% of salmon can go up each dam, right? That's pretty high. And the same thing with the downstream. The facilities there in that order of magnitude, the passage rate. Now, trap and haul has been a little bit more mixed and a little bit more variable, right? And so there's still a lot of work to be done. And of course, you're handling fish, which introduces stress. So that's another aspect you need to look at more carefully. Now, is there any hope for other species? Well, I'm giving you one example from Spain, this one. So back when the first, one of the first meta-analysis that was mentioned yesterday was done, non-salmonids were about 21% efficiency, right? But the Spanish built more, with more knowledge about Iberian barbel, for example, so on, geared the design to them, and now it's about 72%. So a significant increase. So again, it tells us that if we can design for the species that and we have enough knowledge about it, we can improve the design. So there is hope to improve designs if we know enough about the species and the conditions and so on. So that's essentially what I'm trying to say. So with knowledge and experience, we can get better at this. Now there's the other category of measures that have also been mentioned, especially this morning with bubbles and so on. It's what we call behavioral systems, and that can take form in terms of light, sound, what have you. And there's a fair bit of research in not only single signals, but maybe multimodal signals. So for example, there's, at least in the middle there, sound, recent references on sound, on light, electricity, acoustic and light bubbles and so on. Fairly recent information, right? And again, some of these facilities, as has already been mentioned, is maybe one fish will respond this way and another species will respond in a different way. So we really need to know who needs to go up or down and who responds to what signal. Otherwise, we can be contradicting ourselves. We can put light there and the eel may respond one way, the salmon smolts another way, and maybe not necessarily help. Right? So we need to know a lot more about it before we can actually apply it. And again, some of these devices have never proven to be reliable on their own, but maybe as enhancing physical ones, I think there's better opportunities on that to enhance an existing system, to see if we can improve an existing system. I think there's more potential there. So I also want to see, not forget the bigger picture, because we're talking fish passage only in this part, but fish passage is part of the ecosystem in other ways too. It's part of how much flow is in the river. Is the habitat suitable? Can we restore it? It's all those aspects of the river system and the ecosystem that are important, and that's what we include in ecohydraulics, right? And ecohydraulics is a fairly recent science with attempting to bring ecology and biology with hydrology and hydraulics and geomorphology together. And even the term was coined in the 1990s, so it's not that old in a sense. And a lot of sciences and interdisciplinary stuff take time to develop. But it's very encouraging that in the last few decades, we have seen essentially an exponential growth in research and publications on ecohydraulics. So that's a very encouraging. A lot more people are involved, a lot more people are publishing, a lot more people are looking at things much more carefully, which is the good scientific way to go. So, major point here. No matter what facility you may use, attracting fish to find it or guiding them to find it is probably the most important design aspect that you're going to have. So anything you can do to help that is paramount, essentially. So, and this is where we're weakest on our science part, I think. And not a lot of studies have concentrated. They're not easy to do, but we need to do better. And here's an example from Hell's Gate in BC, and it goes back almost 100 years. This was a canyon. So it was difficult for sockeye and other salmon to go through, mostly sockeye. But naturally, they would go up, and maybe in some years when it was very high flow, a lot of them wouldn't necessarily make it. But when they were building the railway, there was a landslide, so it became narrower. So a lot more higher velocities, turbulence, flows, and so on. But back in the 40s, they started, this is where the first vertical slot was actually developed. because you have the river going up and down by 27 meters. And there's no dam here, right? It's just a narrow canyon. And you can see there that in order to help fish find it, they have fishways on both banks, not only for a certain height, about 10 meters in each one, so vertically they can cover a lot of ground, and even horizontally, they're not all placed at the same level. They could be up or down a bit. And you can see that at the very low flows, the low level fishway, for example, when the river is at very low flows, there's even a small structure over here on the side of the bank to cover smaller flows. So lots of different vertically and horizontally kind of aspects to cover it. So a lot of fish find it, but it doesn't mean that all of them do. And actually, as the latest meta-analysis, but somebody mentioned it yesterday, Hersey 2021, essentially says that for most species, finding and entering the fishways may be the most challenging task. Passing is easier. And actually, that's what they found here with some early telemetry studies, that about, if I remember correctly, something like 75% of the fish would find the fishway, but 100% of them, once they found it, entered, they would go up. So the challenge is finding the fishway for in this case, or you can also apply it for downstream. So how do we improve our information on that? And here's sort of trying to illustrate the point I was trying to make with nature-like fishways on the left. The fishway entrance is a little further down. So they found that attracting them was more challenging, and exiting for that matter, but ascending it, going up, was fairly easy for these fish. And these are small species, Colorado pike minnow and a couple of suckers, right? Different, no salmon or anything like that. But we were talking earlier about turbulent kinetic energy and Reynolds stresses and stuff like that. Is that relevant? Because we have a lot of laboratory studies in that, but can we observe that in real life in a structure in the field? And that's what the Seton Dam in British Columbia. This Seton River is a tributary to the Fraser, to the large river that, well, Hell's Gate is much further downstream. And actually, the purpose of it is to divert some water to a smaller hydro project on the bank of the Fraser, not blocking the Fraser, but on its bank by BC Hydro. So here, and actually I have visited that site way back when I first started in the business. We had a field trip in BC, and we looked at that. The main point is that traditionally, this is how what's marked SSV1, that's how they spilled the fishway, and this is a vertical slot, by the way. And they were spilling the water there to attract the fish to find the entrance, right? And that's how they did it for many decades. Then there was a biological study that said, you know, some of these fish seem to be stressed, or some of them may not reach their spawning grounds. Why is that? So BC Hydro allowed them to do this experiment. Okay, what if we spill the water over here, SSV4? We call it scenario 2, the first one scenario 1. The hydrodynamics below are quite different. And actually, I first ran across this project when I was doing consulting work for Iceland. And I said, okay, they explained that biologically there was a problem, but they didn't explain hydrodynamically what was the problem, because the engineers were a little slower than the biologists publishing their results. So that was happened in 21. So that's the study now that gave us, they did CFD modeling, they did all of that, and they checked turbulence kinetic energy and Reynolds shear stresses, and they outlined how the fish, this is the velocity pattern when the attraction flow is very close to the fishway entrance, and this is the velocity when it's away from further away from the entrance. So you can see the velocity is very close to the entrance, which is down here, is very high. Fish had to go through very fast water and turbulent water to find the fishway, while here, much easier for them. They still would find it. And the same thing, they tested turbulent shear stress and turbulent kinetic energy. And these are some of the values they came up with that could correlate with their movements for these sockeye salmon. And you can see the sizes of those. These are adults that go up. So again, some of these hydrodynamic variables, before we used to think, okay, velocity, and that's it, right? And distance maybe, or some. The turbulence and the hydrodynamics play a big role too. So in this case, they found that actually about 10% of that population with the original spill close to the fishway were stressed out enough that even if they reached their spawning ground, they wouldn't spawn. So it had an effect, right? Another way of passing, of course, we mentioned is, and there is a lot more work needs to be done in this area too, is over a spillway. And so a bad example of how to do that, right? But there may be good ways to do that if we study it enough, because how the flow accelerates, there may be a way to guide the fish down with proper acceleration, just like we're trying to guide them into a bypass. So there may be ways to do that well. And actually, the illustration there was done by Jennifer. Wasn't too, I forgot to put the name down. And it's essentially different species will respond differently, but maybe the velocity gradient seems to be very relevant in a lot of studies that have the special velocity gradient seems to be important. And in this case, we're trying to compare a traditional spillway which has a vertical face versus one that has 45-degree face. And the 45-degree face actually helps quite a bit, not only with the flow, but as we found out with the fish as well. So that's another aspect. Of course, we have other ways of looking at downstream too. So avoiding turbines is one option, of course, and bypasses is one option to try and help them avoid the turbines. The other part that has been some work on bar racks that normally are there just to prevent debris from ending up in turbines. Can we design those to at least help the larger fish, not the tiny ones to go, the small ones to go through, at least the larger fish not to end up in turbines, right, and guide them elsewhere. Archimedes' crew has been mentioned, and actually on this trip last week we visited Syracuse, where Archimedes was very active when it was a Greek city then at that time. And turbines have, existing ones have been modified, like the Kaplan, for example, to be better for higher survival. On the Columbia River, for example, they have applied that. But there's new designs also, the helical design, which hasn't been tested in the field yet, but laboratory results seem to be very favorable, whether they can, a lot of fish can survive, even long ones like eels. Okay. Another aspect, of course, we need to look at more carefully is swimming performance. And of course, there's different ways of measuring things, and you can, how to interpret the results might be a bit of a challenge. Whether you put them in a treadmill in a lab or in an evolutional channel in a real river. And the results, we put together a big database that some of you are aware of. And these, we were able to sort of group species by categories, like depending on their swimming modes as well as species. So the ones that have the majority of the data, which gives you very good trends, is this subcarangiform, which includes salmon and walleye and many other cyprinids, for example. You can see the families listed there. And the eels and lamprey, which is the anguilliform swimmers. So they have pretty good data, give you overall trends, which can be helpful. And these are other groups that are missing some of their data. Like the carangiform swimmers, for example, you can see data on the burst range, the higher speeds, but not much data on the longer sustainable speeds. The same thing with the sturgeon is actually the opposite. We have reasonable data on the sustained lower velocities, but not on the burst, although there's been some recent studies that help in that respect, and then some other species as well. Now, what can we do with that? We have to realize that, the variability that you saw in some of these curves, right? You see a lot of variability on the curves. It's actually real even for a single species. Atlantic salmon from Norway, recent study. They tested all these different sizes of Atlantic salmon in the same equipment, the same temperature, everything the same. But look at how they came up with results. The average swimmers versus the best swimmers and the worst is quite a variability, and does increase with length, the speed. So a lot of this data is variable. That's the main message I'm trying to get. So even in the big database that we analyzed, yes, the variability is there. So then what do you design for? Is it the average swimmer? Do you want to those are the questions you have to deal with, right? But there's still good information. And of course, we can do a lot more with that database. We just did some basic analysis. There's a lot more. And of course, this was done back maybe 10 years ago. So there's a lot more references since then that can be done. So that's another aspect that people can look at. And here's some more recent data set. So what we put together is a tool you can find on the web, and you can actually use it. And the curves from it are from that tool. But then on that, we superimposed the data. A couple of people are here, right? Costa is here. Paul is here. They were involved in this. 2020. And here the points are from that eel study, right, on swimming performance. And they seem to fit reasonably well. Maybe they separate a little bit by temperature, but they're in there. And all we did is the curve, the lines are from our big database. And you can go do it yourself if you like, if you go to that link. Of course, that's still simplistic because you're only looking at velocity and speed, but agent-based models or individual-based models that already have been mentioned is another way to become more sophisticated in this area, right? How do you model movement and so on? And the most recent one, I don't know if nobody has mentioned it yet, Goodwin 2023, the last one listed there. They actually did some of the more detailed modeling with salmon from California, I believe, and their migration patterns. And they included not just velocity, but turbulence parameters and other things. It's a good critical review of this area. And I suggested it to Rachel. Okay. So there's progress being made, but we still have a lot more progress to make. So overall now, avenues for improving fish passage. So for effective fish passage solutions, including dam removal, and nature-based solutions that we seem to like better, of course, we need research, not only in the laboratory, but in the field. And a lot of times that's where we're lacking, the field data, because it's more difficult, more expensive, what have you. But without the real world examples, the lab may not always represent reality. So we need that a lot. And again, adaptive management philosophy. I made the point that attracting and guiding fish is probably the most important thing that we can do to improve any fishway or any passage facility, upstream, downstream, and so on, to improve the effectiveness. And of course, we need a lot more work on especially species other than salmon. Even in some cases that we need some, but for other species, a lot more need. And now that we're starting to understand a little bit about hydrodynamics and stimuli and so on, can we also understand that better, but also supplement it potentially with some of these behavioral stimuli that might work with different species to come up with more effective solutions. So how can we start? I mean, because projects are still going on, right? So we still have to build something now. Maybe 10 years from now, we'll know something better. But we can start with what we know and use the best information we have. There's usually some guidelines out there, but they have to be suitable for the species that we're concerned with, not just salmon, right? And we still need to collect some basic information even on the specific site that we're working with. And that can be hydraulic, biological, of course. And another tool we have these days, and we can use it well, and it was mentioned too, CFD. We can simulate things quite well, and that can help us design it better, right? Because we can put some thresholds in there, some things that we think those specific species are, it's important to them, then we can translate it into design. And then implement the most suitable option, but don't forget about installing it properly, because sometimes construction issues come into play too. and of course evaluate its performance, or at least some of them, over many years, several years, not just one or two, because the natural population of fish vary over years too. So how can we decipher what's important or not? We need several years of data. Combining physical and behavioral might be one way also to offer some improvements. And in large areas, remember, those tributaries way up, and I don't know if in Europe you may have to go, I don't know, to high mountains like Switzerland, or I don't know if in Italy there's some high enough mountains that have tributaries that have much cooler water that might be helpful further down when, especially climate change, warms things up. But in that case, if there is a barrier, maybe a facility like a lift or a drop and haul might also serve the purpose of helping with water further down to keep fish survival high. So, concluding now, ecohydraulics covers a lot more than fish passage only, and integrates a lot of interdisciplinary knowledge, and we have proof in some cases at least that it can lead to innovative and practical solutions where we're concerned about environmental issues and environmental mitigation and so on. But of course there are still tremendous challenges, but also that creates opportunities for researchers like you, and hopefully a lot of you will continue to in this area, and there's a lot of work to be done, and in all these areas that ecohydraulics covers. And at least in the past, a lot of times, let's say fish passage facilities or any other mitigation, flows or what have you, it was an afterthought. The project was done, maybe, okay, if we're having a new project, that's the time to build everything, to consider everything at that time, because then you have the opportunity to develop it the way it could be done, as opposed to modifying something which limits you in many ways to achieve the best result. So, habitat restoration, river flow management, and passage of, and a lot of times we emphasize fish, but there's other organisms, aquatic organisms that we need to remember as well. And a lot of times by those three elements, there's synergies. So if you have environmental flows, maybe that's partly your attraction flow for the fish passage facility, for example, and so on. Well, if you're going to restore the habitat, maybe that can also help guide fish. So it's those things, if we look at the bigger picture, then it can be also helpful in that respect. And lifelong learning is not a new idea. It's been there for thousands of years. And you graduates, I hope you follow up and you have your own eureka moments coming as well, if you haven't had them already. Thank you very much.